in the main A level, you worked out the angle between two vectors using a triangle and the cosine rule. So we will work out this angle here. In the further maths A level, we generalise this a little bit and we look at other ways of calculating the angle. So what we're going to do in this video is we're going to take the cosine rule and we're going to use it in as general a form as possible, and we're going to try and calculate this angle theta. Now what's going to happen is we're going to end up with this gnarly little bit of I guess it looks like algebraic manipulation, but it's a quite nice little rule which as mathematicians we tidy up to be the dot product. If you want to know how the dot product works, this isn't the video for you. What you need to do is go and check out the videos that I've got on my website or the rest of the videos in this series to look at how the dot product works. I'm just going to prove it in this video. Okay, so we're going to do this as generally as possible, which means I don't want to introduce any concrete example at all. I'm going to keep this in terms of algebra. So I'm going to label this vector as A1, A2 and A3 to represent I, J and K, and this vector OB to be B1, B2 and B3. Now I need my third side of the triangle. I'm going to need A to B, which we know is B minus A. And I can now write that in terms of its I, J and K ordinates as well. So this one is B1, B2, B3. This one's A1, A2, A3, and thus A to B is B1 minus A1, B2 minus A2, and B3 minus A3. Okay, to use the cosine rule, I need the lengths of these lines. I don't need their vector form. So I need to work out the magnitude of the vector OB, the vector AB, and the vector O to A. I'm just going to write those out. Pause the video if you are wanting to do these for yourselves, but just to save a little bit of time, I'm going to go straight for what the answers are. So O to A is the square root of A1 squared plus B. It's not B, is it? It's A2. There's my brain running away with me. A2 squared plus A3 squared. This one is the square root of B1 squared plus B2 squared plus B3 squared. And A to B is a rather gnarly little expression, which just comes from squaring each of these terms, adding them up, square rooting them, so Pythagoras in 3D, and expanding those squares out. So we end up with B1 squared minus 2A1B1 plus A1 squared plus B2 squared minus 2A2B2 plus A2 squared, and the same with the 3's. So I know using the cosine rule then that for the angle theta, AB squared, which is something I know, is OA squared plus OB squared minus 2 OA OB cos theta. And I'm just going to write all of that algebra out. So the expression I wrote on the last slide, squared, just gets rid of the square root. So I'm left with the B1 squared, the minus 2A1B1 plus A2 squared, and I'm going to get the rest of that expression, like so. So now I can try and do quite an epic cancel of all of the terms that are common. So I can take off B1 squared from both sides, so that can disappear. B1 squared's gone. I can do the same for B2 squared, which is there and there. I can do the same for B3 squared, and I can do all of my A squareds as well. So A1, A2 squared, and A3 squared. That leaves me with minus 2a1b1 minus 2a2b2 minus 2a3b3 equaling minus 2. Now I've left these alone because those, in theory, if we know what our vectors are just numbers. OA and OB, just numbers, they sort themselves out. I can factorise out a minus 2 from this left-hand side here, leaving me with a minus 2 as a factor on both sides of my equation, and thus I can cancel it. Right, so the right-hand side now, that's looking okay. OA is a number, OB is a number, cos theta is absolutely fine. Theta is what I want, so that's great. What I'm struggling to get is this bit, A1, B1, A2, B2, and A3, B3, except for the fact that it's a really nice pattern. It appears to be the respective like ij's and k's of each of my original vectors multiplied together. And it's appeared in quite a fundamental idea. How do you calculate the angle between two lines or two vector lines? So we should probably formalise this a little bit. This little expression here, this a1b1 plus a2b2 plus a3b3 is called the dot product. And it is used precisely for this, for the angle between two vectors, and it's got a couple of nice consequences which we'll look at, and we notate it with a dot, and that is to distinguish it from the cross product, which we use the kind of traditional multiplication for. So we're using another form of multiplication symbol to show the dot product, and that is the like the I components of each vector multiplied together, the j components and the k components multiplied together. In summary then, the dot product, which is represented using this dot multiplication notation here, a dot b, or in the vector form, but either way with this dot notation, is the I components, the j components and the k components multiplied together respectively and then added up. And we got that from using the cosine rule, but the whole idea being that it can be used in finding the angle between two vectors. So this is a sort of neatening up of what we got on the previous slide. A dot b is the modulus of a, the modulus of b, don't forget those are the lengths of the lines, cos theta. And so cos of the angle between those two vectors is the dot product between the vectors divided by their magnitudes. And it's worth pointing out that we worked out this angle for two vectors that are diverging. So this is for diverging vectors. Good, so check out my next video for how else this dot product helps us and some other applications of it.